All right. So we're going to go over homework. You guys just got to tell me which numbers that we're going to go over real fast. Hold on just a second. Let me write it down. 18, 20, 26. Whoa. Slow down. 6 and 8. Can't do all of your homework, guys. Whoa, 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 whoa. Yes, ma'am.
Can you do like 1 since I wasn't here?
I'm doing 5, 6 right now. Okay. What else? 30.
You get 18.
Yeah, yeah. All right, so 6 is just making a chart. So what do we?
Students and staff, please pardon this interruption, but I need to see the following students, please, in the comments area. Ethan Everhart, Savannah Presley, Carter Haynes, Landon Howell, Zachary Klein, Alex Gent, Kenya Garcia Allen, Aiden Seals, Troy Cook, John Applegate.
Guys, I'm recording.
Thank you. Have a great day.
All right, so you had this, you had a chart to make. Your chart was the same one as the other 2 and 4. So when you made your chart, it was the negative 0.1, negative 0.001. Sorry, this should be just 0.01, 0.001. And then we had it going to 0. When you just look at this side, you have 1.05, 1.005, 1.0001. Where is it going to?
How do you put the numbers in the bottom?
You put it in your calculator.
Yeah, how do you put that in your calculator? That's what I need help with. You have to do that.
Okay. So no. Shh. All right. So the first thing that you want to do is important. I'm very sorry. Guys, I'm recording. Sorry. We're going to do alpha y equals. And then ln is beside the 4. So ln.
I'm good now. Hey, Bessie, for that.
Hey, I'm recording. X plus 1 over x. And then, I'm sorry, you can't see this calculator. I need to get one of the, there it goes. It's a little better. So then remember your table set. So second window, we're going to change to ask. Is everybody okay with that? And then when I look at my table, there's not going to be anything there because you haven't put anything in. So negative 0.1, negative 0.01, negative 0.001, because we're going towards 0. But you guys can see within the first 2. If we put in 0, we're going to get that error. Sorry, 1.001, because that would be next. You guys can keep putting those values in. So once you put them in, just in the top 3, you can see that it goes to 1. And this one is a crappy number, and you can put it into your calculator if you need to. This way, or even graphing them, is a better way to do it. Like that definition is ridiculous. So I would never do it that way. So this one's literally just putting it in and seeing that it goes to 1. Welcome back. I'm recording, so I just wanted to be honest with you guys, make sure you know. Same thing with the next one. We have x plus 4, and then on the bottom, we have x squared plus 9x plus 20. When I go to my table, the values that you wanted to put in, and this is probably where it was a little bit rough for you is making these values. You just got to think backwards because they're negatives. So we started with negative 4. We need values less than negative 4, but that are really, really, really close. So it's going to look just like this chart, except you're going to put a 4 in front of it. And on the other side, you'll have the 4 in front of it and put the values. So negative 4.01, negative 4.1. On this side, negative 3.999, negative 3.99, so on and so forth. And like I said, if you can get one side in, negative 4.1, 4.01, and negative 4. Oh, below and above. So your limit is right here. We're looking for negative 4. So what's happening? And these are really crappy values, but if you guys put them in, so it's 10, 100, and 1,000. So let me go back to my table. 10 over 9 is 1.11. And then it had, did I have 100 over 99? And then I think it's I don't know what it had. 999. So what are we going to on number 8?
Please pardon this interruption. I need the following students to report to the office. Zoe Byerly, Stephanie Cabrera, Alan Cachette, Maya Clement,
I'm recording.
Hope Davenport, Brianne Blankenship, Stephanie Hernandez, Elizabeth Blankenship, Leela Craven, Carmen Kinley. Thank you.
All right. So the limit as x approaches 0 of secant x, what is secant? You guys have that in the front of your book if you need to look. One over cosine x. Okay.
So you can't compare on a secant x?
I mean, I don't have a secant on my calculator, so probably not. But if you use Desmos, you can, but you can't use Desmos on the AP exam. Okay. So on this one, I'm going to change it back to auto. And I'm going to look at my value as it goes to 0. What's your value at 0? That's it, y'all. So you can look at your table without having to graph your table.
Can you look at it on the graph and see where it just goes to?
You can. It's a little bit harder with some of these, but yes.
I did a graph last night.
Yes. Yes. 20, let me look at it because I don't know that I copied it right. I mean, I copied it right. I just don't know what the question is. Is this 2.2? Said, I didn't hear what you said. Sorry. Yeah. 2.2. I didn't write anything. It's nothing past
Yeah, right there.
Oh, the top. I'm sorry. Okay, so 20 has the limit of x approaching 1 of f of x. So if we look at that, we're just looking at the graph. We're looking at the graph. And we see that that open circle is at 1, 4. So on 20, your limit as x approaches 4. I'm sorry, not approaches 4. Approaches 1 is equal to 4. And again, it's because that graph has that point 1, 4. And again, it doesn't have to be a real value. Okay, it can be an open hole, but that's where it goes to is 4. So there's 20. 26. All right, so when we look at this graph, all right, 26 says f of -2. That just means plug in -2. Okay, so if I plug in -2, where am I at on this graph? What's this dashed line for? It's undefined, it's a horizontal, I mean, a vertical asymptote, right? So what is the value of -2? It doesn't exist. Does everybody understand that? There's no value of -2. So then we talked yesterday, if we look at -2 on both sides, today we're gonna, I don't know if it's today or tomorrow, we're gonna start left and right. I think it's today. This one goes to -infinity. This one goes to positive infinity. Since they don't go to the same thing and it's unbounded, the limit at -2 does not exist. Now, if they came to the same point, it would exist. Once we split left and right, it will exist. Does everybody understand that? So for right now, it's coming two different ways. There's no limit at this point. All right, f of 0. What is your coordinate at 0? We're not talking about the open circle. We're talking about the closed one. What is it? 4. The limit as x approaches 0, because you have two graphs and there's a jump, it's not just a point. So like on the one that we did a minute ago, we had that dot. Remember, that doesn't bother your limit at all. So you ignore it on your limit. But on this one, you have a graph on either side. So you have to look at both. And since there's graph on both sides and there's a gap, this one does not exist. Now again, this one will exist when we do right versus left. But when we're doing the whole limit, it doesn't exist. All right, then we have f of 2. What's the value at 2? Why? Is that open circle, so it doesn't exist, right? But what's the limit? What's the limit as it approaches 2? Remember, the whole doesn't matter for the limit, right? Where is that whole at? Where's the whole at? What's the coordinate? Like 0.5. It's 1/2. All right, so then f of 4, when we go to 4, what's your value at 4? 2. We do have a dot, right? So that does exist. But what about your limit as you approach 4? Does it exist or no? Why? There's no bound, right? It just keeps going up on both sides. Y'all understand that? Everybody good? What part? Which one? No, f was 1/2. No, it doesn't exist because it's a whole. It's okay. All right, so guys, if you have a question, don't make a comment about it, ask the question, okay? So one more time, what they're getting you to understand is the limit doesn't have anything to do really with the point itself unless it's an actual point. So if we go over this again, -2 is a vertical asymptote. So there is no value that matches -2. So that one did not exist. At -2, here's your -2. We have a graph going up and a graph going down. That is not a limit, okay? It will not exist. That happens again when we look at 0, there's the gap. Does everybody see that? So there's no limit there either. When we look at +2, there's an actual point there. Even though it doesn't exist, it does go to that 1/2. Does everybody understand that? So that's why that limit does exist. And then at 4, it goes again up like this. It's unbounded, so it doesn't exist. Is that a little better? Okay, so anytime it's opposite ways or unbounded, period, up or down, there's no limit. If there's a break, there's no limit. If there's a hole, there is a limit. Okay, maybe that'll help a little bit. All right, so that was 26. 28. I want y'all to hold off on 28 again because it was piecewise and it's trig, and we will go over that. So that's one that I definitely need to go over with you, but I'm not going to do it yet. And I Did not do. Did I give you 30? Oh, I don't want y'all to do that because it's sketching. So just mark that one off. So sorry about that. Again, your homework is what Ms. Burkhardt assigned her class, so I just followed through with that. And if there's anything that I see that's weird, I just kind of don't worry about it. All right. Everybody good? All right. Get your notes out for today. Guys. We're going to talk about evaluating limits analytically. Guys, I honestly need you to stop talking. So we're going to start with properties of limits. In section 2.2, you learned that that time limit, I think that should say the limit. I don't know what that is. I'll have to fix that. Of f of x as x approaches c does not depend on the values of f at x equals c. It may happen, however, that the limit is precisely f of c. So in such cases, the limit can be evaluated by direct substitution. So sometimes whatever c was actually what our value was. Okay, so that's all it's saying. There are times that you can do direct substitution, which means you can take that c and plug it in for x, and you can get your limit. All right, so again, the limit as x approaches c of f of x could be f of c. Those functions are called well-behaved functions because they are continuous at c. All right, so all of those do not exist functions that we just had where they were unbounded or they had the gaps. Those are not continuous. How do you know if it's continuous? You can keep drawing with your pencil without picking it up. Okay, that graph that had that gap, I would have to stop, pick up my pencil, and go again. That is not continuous. Does everybody understand that? So if it's continuous, then you can absolutely plug in C. So theorem 2.1 has some basic limits. Let B and C be real numbers and let n be a positive integer. So we have the limit as x approaches c of b will equal b. So if they give you the limit of 5 as x approaches 4, the limit of 5 as x approaches 4 would be your c, then your answer is going to be 5. It's a continuous horizontal. Okay, we'll see examples of this. So I'm just trying to give you an idea of why it would say b and b. All right, 2, the limit of x as x approaches c can be direct substitution where you plug in that c. So if we had the limit of x as x approaches 2, then the answer would be 2 because we just plug in 2. And then the limit as x approaches c of x to the n. Sorry, that should be an n. Equals c to the n. Any questions? So far, so good. All right, so here's your examples. Here's what I was trying to explain to you. If you just have a value right here, so limit of 5, limit of 3, limit of 4, limit of 3 as x approaches 2 is just going to be 3. Remember yesterday we were graphing them or we were looking at our table. When we look at our table and we get to our value of 2, everything is at 3. So it has to be 3. Does everybody understand that? So that is why if you have just a constant value, your answer is going to be the constant. This one, the limit as x approaches -4 of x. Again, I'll show you in your calculator. We look at our table. As we approach -4, what's our answer? What's our y? It's direct substitution. So you're going to plug that in for x. Don't make it harder than what it is. It is that easy, okay? So don't be like, oh my God, it's calculus, I can't do it. No, it's super easy and you can, okay? This one and the next one have been very easy homeworks that I feel like are very easy. Are there problems on there that are a little bit struggle problems? Sure. And we'll go over those. But for the most part, they're like, oh, here it is, here it is, here it is, okay? The next one, same thing, we're going to use direct substitution. So we get 2 squared or 4. Is everybody okay so far? Pretty simple. All right, theorem 2.2, properties of limits. Let b and c be real numbers, let n be a positive integer, and let f and g be continuous with the limits f of x approaches c is L and g of x. Sorry. G of x equals k. All right. So the first thing is scalar multiple. So that scalar multiple is if we have the limit as x approaches c. The scalar is just a constant. B times f of x. So your limit would be b, whatever that scalar multiple is, times your actual limit L. The next one is sum or difference. I'm not going to write out the whole word difference. If you want to write it out, go ahead and do that. That would mean as the limit of x approaches c of f of x plus or minus g of x would be L plus or minus k. You know that the product is multiply. So we're writing the same thing. The limit as x approaches c, f of x times g of x is going to equal L times k. Quotient means divide. Y'all, it's the same exact thing. The limit as x approaches c of f of x over g of x equals L over k, but k cannot equal 0. K can't equal 0 because we can't divide by 0. And then the last one is the power. The limit as x approaches c of f of x to the nth power is equal to that limit to the nth power. Very good. All right, find the limit as x approaches 2 of 4x squared plus 3. This is like breaking it down a lot. There's no point in really breaking it down like this, but I'm going to go ahead and do it anyway. This 4x squared plus 3 is the same thing as the limit approaches x to the second, x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. This again is just using the properties. You do not have to do it like this. Okay, it's just showing you those properties. We can split this up into 4 times x squared. So 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. Again, I would never split it up like this, but you can. But they just want you to see all those properties. So this would be 4 times. What do we do to this one? How do we get the limit of x squared as x approaches 2? Yeah, just plug it in, 2 squared. And then plus, what's the limit of a constant? The constant. So we get 4 times 4 plus 3, which gives me 19. No, realize you can plug that 2 straight in. So what's 2 squared times 4 plus 3? I don't have to do all this work. Okay, so don't look at that and be like, oh my God, that's a lot. You don't have to do all that. That's just showing you those properties that we just worked with. Okay, so take it out of your brain now. If P is a polynomial function, again, if P is a polynomial function and C is a real number, then the limit as x approaches C of P to the x equals P to the C, or P of C. If R is a rational function given by Rx is equal to Px over Qx, and C is a real number such that Q of C does not equal 0. Remember, we can't divide by 0. Then the limit as x approaches C of R of x equals R of C. There's a little bit more to this, but I'm trying to get you caught up. Remember, we defined R of x as P of x over Q of x. So it would be P of C over Q of C. I like. Okay. Absolutely. You're welcome. Take all this. Did not say take your stuff, so I don't think it has to do with that. Is everybody good? All right. The limit of a rational function, all this says is just plug in C to your function. We're going to find the limit of x squared plus x plus 2 over x plus 1. Remember, our denominator cannot be 0. So that's the first thing you need to do is look to see if your denominator is 0. If it is 0, you have to fix it before you take the limit. So that will be the hardest stuff that you do is fixing that denominator before you take the limit. Otherwise, just plugging it in. All right, so this one, if I plug in 1, what's 1 plus 1? So we are good to go. All we need to do is plug in 1 squared plus 1 plus 2 over 1 plus 1. We're plugging in our limit C. 1 squared plus 1 plus 2. 1 plus 1 is 4 over 2 is. That's it. And again, we can do that direct because our denominator is not equal to 0. Okay. Any questions? I don't know why I have a bunch of space there. That's all that is to that problem. A lot of your homework. That's all there is. Okay. So theorem 2.4, the limit of a function involving a radical. Let n be a positive integer. The limit below is valid for all c when n is odd, and valid for c greater than 0. Remember, it's positive when n is even. So the limit as x approaches c of the nth root of x will be the nth root of c. Direct substitution. That's all they're telling you. Plug that limit into the function. And this one just happens to be a radical. So it uses a square root or a cube root or a fourth root. And then same thing with a composite. If f and g are functions such that the limit as x approaches c of g of x equals L. Same thing for f of x. Then, don't know why this little slash mark is there. Don't worry about it. The limit as x approaches c of f of g of x is equal to f times the limit as x approaches c of g of x, which is the same thing as f times L. Now, on my composites, I don't ever do that. I just plug them into each other, direct substitution. Okay, so don't let it look complicated. Don't let it look complicated. Okay. Any questions on that? So here are some examples. I have 6 examples that we're going to do. They're really quick. The first one is the limit as x approaches 0 of x squared plus 4. What do we do on this one? Plug in 0. 0 squared plus 4 is 4. The next one, the limit as x approaches 4 of the square root of x. Did I write them out on this last one? No. So this one, the limit of as x approaches 4 of square root of x. What's this one going to be? 2. Remember when I said your homework is really quick? That's a lot of them where you're just plugging in like that. Okay. The limit as x approaches 0 of the square root of x squared plus 4. Again, as long as it don't give you something weird, we're in good shape. Like you wouldn't want an imaginary here or anything like that. So plug it in. 0 squared is 0 plus 4 is 4. The square root is 2. So these are your composite functions. We put one into the other. Okay, so that's why it says limits of composite functions. So then we have 3 more that we're going to go over. The limit as x approaches 3 of 2x squared minus 10. Literally plug it in. What's 3 squared? Times 2? Minus 10. That's it, yeah. Your next one, the limit as x approaches 8 of the cube root of x. The cube root of 8 is 2. And then the very last one, the limit as x approaches 3 We're gonna plug them into each other. The cube root of 2x squared minus 10 is equal to, do that direct substitution, 3 squared is, times 2 is, minus 10 is, cube root of 8 is 2. So this is just them trying to do, like if I went back and said f of L. So you could do that, but I feel like direct substitution is a lot easier than trying to use the properties, if that makes sense. Okay. So why make it more complicated than it needs to be? All right, let's C be a real number in the domain of the given trigonometric function. Now these will come in handy, okay?
Please pardon this interruption again. We do not know how to do this any faster. We are sorry. I need to see the following students in the office. Luke Niebrick, Luke Williams, Sarah Chavez, Johnny Hernandez, Sarah Kuntz, Hector Marietta Rocamato, Madison Patrick, Caden Pless, Lillian Wood, John Watts, Destiny Weaver, Anton Williams, Samuel Phillips, John Applegate. Thank you.
They're gonna ask if they were in.
Hopefully not. Again, most of you are gonna say no now because we're both wearing masks, right?
Yeah.
So there you go. So you might have been right next to him, but you're wearing a mask, so you're good to go. They will slow down. Remember, these are still residual cases from when we didn't wear masks. So
The only
it'll
time
slow
really
down.
is the mask one.
All right, so I'm just writing them all down. So sine, cosine, tangent, cosecant, secant. And again, it's just direct substitution. Cotan. So again, still direct substitution. And then the last two, still the same thing, direct substitution. Limit as x approaches c of a to the x would be a to the c. And that a greater than 0 just means that it's positive. A has to be positive. And then 8, the limit as x approaches c of ln x would be ln c. Everything is direct substitution. We've done nothing else. All right. So then it says find each limit. So we're going to do direct substitution. You have a tan key on your calculator. I'm going to go ahead and tell you that it's 0. Literally plug it in, tan 0 in your calculator. When you put this one in your calculator, I'm going to rewrite this one for you so you can see it. The limit as x approaches 0. You would put in like this, sine x squared. So you would do sine of 0 squared. It's still going to give you 0. Same thing on this one. X is -1 times e to the -1 will give you negative e to the -1. Now that you can reduce to a number if you want to, but you don't have to. You do not have to reduce it. You can leave it just like that. So all I did was multiply e to the -1 times -1. And then the last one, ln x cubed. Again, you can just put it in ln e to the 3. What do you know about ln and e? So we evaluated it to be 3. Have we done anything hard? No, that's what I'm trying to tell you. It gets easier. So the way that they taught limits yesterday was kind of awkward because it's graphing and tables. But when you direct substitution, it's really easy. When we get to left and right, you're going to go back to those. I don't really use tables. I like the graphs. Okay, we can use tables as well, but you'll see. All right, 2.7, let C be a real number and let f of x equal g of x. For all x not equal to C in an open interval. If the limit of g of x as x approaches C exists, then the limit of f of x also exists. And the limit as x approaches C of f of x is obviously going to equal the limit of g of x as x approaches C. All right, so now we're going to get into the ones where your denominator gives you 0. Okay, so what do you have to do? We'll talk about that in just a second. Everybody good here? All right. So find the limit. When we plug in this 1 directly, 1 minus 1 gives us 0. So we can't do direct just yet. We've got to fix it. So if you're terrible at factoring, you're going to have trouble with this. Okay. You need to know how to factor. They're going to give you easy stuff. They're not going to give you hard stuff. So we need to make sure we're not on our phones and we're paying attention. So on the top, we have perfect cubes. Okay. So I told you guys how to do that the other day. I think it was you guys. I can't ever distinguish between you and pre-cal. So if we have x to the third minus 1, the way we factor is you take the cube root of x cubed and the cube root of 1, and you keep the sign. So your first factor is x minus 1. Your second factor is you square the first one, so x squared. You change the sign to positive. You multiply them together. 1 times x is 1x. And then you square the last. 1 times 1 is 1. So we're going to change the top to x minus 1, x squared plus x plus 1, all over x minus 1. Now we have the same thing on the top and the bottom. So what can we do? And now because we don't have 0 in the denominator, we can do direct substitution. So then we do 1 squared plus 1 plus 1. 1 squared is 1 plus 1 plus 1 is 3. That's it. So you've got to know how to factor, okay? You have to know. A strategy for finding limits. These are pretty decent sentences, so at least 2 3-liners, so be ready. Learn to recognize which limits can be evaluated directly. So again, learn to recognize which limits can be evaluated directly. So which ones can be evaluated directly? The ones that don't give you a crappy 0 in the bottom. Okay, so right now, direct is the way to go. All right, number 2, this is the longer of the 3. When you can't direct, so when you can't directly substitute, try to find a function g that agrees with f all x other than x equals c. So that's what we did. We factored it so that we could get rid of that one part of the function where it said we divided by 0. So that's exactly what we did on part 2. You can use the graph or table. To reinforce your conclusion. So again, if you're not sure if you factored it right or you rationalized the right way or did it right, then use your graph or your table. Check it out. All right. So again, dividing out technique factor, we're factoring. So this is math 3 rationals. So we have x plus 3 on the bottom, but when I plug in -3, it gives me a 0. So I know I need to factor. If it doesn't give you a 0, don't do anything. Okay, just plug it right in. But this gives me a 0 in the denominator. So I need to factor the top to see if I can cancel. I should be able to. What are your factors of -6 that add to 1? +3, -2. On the bottom, I have x plus 3. So again, we know that x can't equal -3. That's that part 2 where it agrees with everything except for x equals c. Okay, so that's the part they're looking for. We cancel out. We get x minus 2. And then we do direct substitution. -3 minus 2 is -5. All right. A lot of filling in the blanks. And then this next problem is the crappy one. Okay, you'll do this a bit. A couple problems in your homework. In the last example, direct substitution. Produce the meaningless fractional form 0/0. That's an indeterminate form. So we got 0 on the bottom. We have gotten 0 on the top as well. So an expression such as 0/0 is called an indeterminate. Form, because you cannot, from the form alone, determine the limit. When you try and evaluate a limit and encounter this form, remember that you must rewrite the fraction. Rewrite the fraction so that the new denominator does not have 0 as its limit. One way to do this is to divide out like factors. Which is what we've been doing. What the crap is writing? Another way, gosh, is to use the rationalizing technique. This would have been pre-cal. That's when you would have learned rationalizing. So the rationalizing technique, another way to find a limit analytically is the rationalizing technique. Which involves rationalizing the numerator of a fractional expression. Recall that rationalizing the numerator means multiplying the numerator and denominator by the conjugate of the numerator. For instance, to rationalize the numerator of square root x plus 4 over x, we're going to multiply the numerator and denominator by the conjugate of square root x plus 4, which is square root of x minus 4. So you just change the sign. So it's typically going to be things that you can't factor, okay? Usually square roots in your homework, there's some e's, same thing, okay? Some of the e's you can factor, some of them you can't. But so if we look at this, we cannot factor this problem, and we cannot use it direct substitution because it gives us a 0 on the bottom. So what we need to do is rationalize, and the way we do that, I'm going to rewrite this so it's a little bit bigger for you guys. Square root of x plus 1 minus 1 over x. We're going to multiply by the exact top, except we're going to put a plus instead of a minus. So square root of x plus 1 over itself. Why do we do it over itself? That reduces to 1. We didn't do anything to the problem. We just multiplied by 1. Remember, when you multiply by 1, nothing changes at all. All right, so then it kind of looks crazy, but it's not. It's really easy. So on the bottom, you just squish them together. X, and I put the other part in parentheses to kind of separate it. So you just squish them together. And then remember, I'm going to show you guys really quick. If you had something like x minus 2, x plus 2, when we work this out, we get x squared. You don't have to write this down. I'm just showing you where it comes from. You can if you want to. Plus 2x. Then we have minus 2x and a minus 4. And your middles will always cancel out. So there's no point in even working on those. Does everybody understand that? So all you're doing essentially is squaring the first and squaring the last. So what happens when I square a square root? It goes away. So we're left with x plus 1. All right. And then we're multiplying the last. It's not squaring it, it's multiplying it. Negative 1 times 1. You guys see that? Everybody good? So that made it a lot simpler, right? Our 1s will cancel out, 1 minus 1. What else cancels out? The x's will cancel out. We're left with 1 over the square root of x plus 1 plus 1. Now when I plug in 0, I'm not going to get 1 on the denominator. Remember that x cannot equal 0. So if you see that, that's what it means. And now I'm going to direct substitute. 0 plus 1 plus 1. What's 0 plus 1? Square root is? Plus 1 is? So our limit is 1/2. Last page. I know y'all are tired of listening to me. Your homework is going to be long, but easy. So it'll be quick. Okay. But I want you to practice as much as you possibly can. All right. Squeeze theorem. If h of x is less than or equal to f of x less than or equal to g of x for all x in an open interval containing c except possibly c itself, and if the limit as x approaches c of h of x equals L, which is also equal to the limit of x approaches c of g of x, then the limit as x approaches c of f of x exists and is equal to L. It's just saying if they're all equal, they're all equal. Okay. These are the ones that I thought we were doing a minute ago. These you need to know. Okay, you have to know these. So the limit as x approaches 0 of sine x over x will always be 1. These are givens that you need to know. The limit as x approaches 0 of 1 minus cosine x over x equals 0. You will use some of these, if not all of them, in your homework. And then the limit as x approaches 0 of 1 plus x to the 1 over x equals e. These are like Pythagorean theorem, they're rules, okay? So there are proofs to them. I would never make you do them, okay? Just know that these are rules that exist. So it says find the limit as x approaches 0 of tan x over x. So when we plug this in, we get 0 over 0, which is the indeterminate form. So we need to fix it. Does anybody know what tan actually is? Don't tell me like opposite over adjacent or anything like that. Look in your look in the front cover of your book if you have it, and tell me what it tells you about tan. See if there's anything we can use. Okay. So we have right here tan x times 1 over x. Does everybody understand what I did? I just split it up. She just said that tan is sine x over cosine x. Well, I'm going to change this. Because the bottoms are interchangeable, does everybody see this? So all I did was flip the denominators, which is perfectly fine because I'm multiplying them. We learned a minute ago that the limit of sine x over x is 1, right? And then I can direct substitute here. And I also get 1. So this one is direct. And it'll give me 1. So what's 1 times 1? 1. So we want to make it look like anything we possibly can to fix it. Those will be the ones that trip you up, okay? But we will go over them if you get lost. All right. If we direct substitute on the last one, it says a limit involving a trig function. We're going to get 0 over 0 is indeterminate. So using those things up there, can I make this look like sine x over x? What does that have in it that's kind of screwing me up? Can I pull that out? I probably could. Watch this one. It's weird. Okay. I'm going to change it to 4 times the limit as x approaches 0 of sine 4x over 4x. All I did was multiply by 1, 4 over 4. Does everybody see that? That's all I did. All right. So then I don't like this. You better get used to this because it's going to happen a lot soon. I'm going to change the 4x's into y's. And I'm going to do the limit as y approaches 0 instead. So that'll change it into sine y over y. So all I did was change all of these to y's. And again, y equals 4x. So that 4x didn't go away. I just changed it to a different number or a different letter. You're going to be doing this a lot. Not in your homework today, but eventually when we do derivatives and antiderivatives, and you're going to be doing this. Integrals a lot. So what is the limit as y approaches 0 of sine y over y? 1. So we get 4 times 1. And what is 4 times 1? 4. That's all we have to do. We changed them to y's and evaluated it as y's. That's it. And we pulled them out to here. So there's the 4s. That's all. Is everybody good? All right. I don't know that there's one like this on your homework. I'm pretty sure it's not. I'm trying. Sorry. All right.
They're a lot harder than this.
Let's just focus on today. Focus on today. Right and left, just bounce it to one side or the other. So no, it's kind of the same, but we're going back to graphing pretty much. So your homework 2.3 is page 87. Two, 3, 98, every other even. Y'all know what that means? 2, skip 4, do 6, skip 8, do 10. So it looks like a lot, but it's not as bad as you think it is. The ones that you will possibly have trouble with are 50, 58, 62, 66. Those are all rationalizing. Okay, so you may be okay, but you may not. 70. Everything else is like direct. This is going to be, you're going to have to do some work on. So all of these, you're going to have to do some kind of work on. 78, 82, 86, I did a table for. So just throwing that out there, 86, I did a table for. 90 is factoring. It's not going to look like it, but it really is factoring. Okay, so let me show you real quick. I don't know what I did with them. Let me show you 90, how to start it real quick. You have there's the limit stuff in front of it, but I'm going to show you. Look at your powers. Those are perfect cubes, right? 3 is a cube. Is everybody good? So on top, you have a perfect cube. So remember how we factor that? We take like the cube root. So it would be e to the x, the same sign, and the cube. So I'm trying to show you how to factor this one, and that's all I'm going to do is show you how to factor it, okay? You square the first one. So there's just squaring it would be 2x. You change your sign. You multiply them together. And then you square the last. So that's how you factor the top on that. That's that cube root thing that I just wrote on the paper.
Yeah, so I didn't know that.
So
At least
No,
you-
that is
Ask
funny, like,
Ask then,
I thought I'd figure it out. No.
but you didn't clearly. So ask then. So again, if you have x cubed minus 8, which is what we had in our problem, you're gonna, what's the cube root of x cubed? X. What's the cube root of 8? 2. So to factor that, you write those two factors with the same sign. So if it was a plus, you would write a plus. You got that part? All right. The next part is you square the first. Write the opposite sign. Good. Multiply them together. What's 2 times x? And then square the last. 2 times 2.
Oh, okay, that's easy, gotcha. I'm like, what do I write that down so I don't forget?
It's on your table. Never mind. It's on your notes.
Just give me a minute.
It's the exact same one for your notes.
Okay, I got it now.
All right. On the bottom, same thing. This is like saying e squared. So I have 2 perfect squares separated by a minus. That's the same thing as having x squared minus 4. How would you factor x squared minus 4?
X plus 2x.
But we don't have x, we have e to the x. So this will be e to the x minus 2, e to the x plus 2. And then these will cancel out, and then it's direct substitution. So everybody got that for number 90. Okay, so that one's the weird one. 94 has those x's and delta x's. So you might be a little struggling with that. Change your delta x's to y if you want to, okay? And then that's it. Everything else you should be fairly good with. I know that sounds crazy, like that was a lot of problems or whatever. But those are all the ones, that's pretty much all that you don't have to do direct substitution on. So everything else is direct. It's gonna be quick. That's what I'm trying to explain to you. These are rationalizing. Check your notes out. I think one of them is trig functions. Very good. All right.